Good afternoon. Your attention, please. Thank you. So I would like to continue with least square regression. To quickly recap what we talked towards the end of last lecture. Generally, data that you collect, one variable as a function of another variable, is acquired in the form of discrete points. We'll call it xi and yi. So you have multiple entries x1, y1, x2, y2, and so on. What is a fit? Can anybody tell me what is a regression or a fit? Regression or a fit expression. Can you tell me in words what does it actually represent?
It's a line that describes how points move, like in the graph.
So I think what you're trying to say is it's a function that we build that describes the trend in the data, right? A function that describes the trend, function that describes the trend in the data. And why do we want to do a regression? Why don't we just handle the original data as it is? Why do we bother to do regression? Easier in what way? You are correct.
Have one individual function that we know how it operates instead of randomized data.
That is a function containing few parameters can replace the entire data set. Like this data set could have 1 million entries or more. We don't want to carry around 1 million numbers. It's much more compact to compress that information in a function which has a fewer number of parameters. And these parameters, how do we get them? How do we get them? This is the fitting process. So I'm going to illustrate that through equations and numbers today. The fitting process involves essentially compressing or summarizing all the individual data points into the fit parameters. So individual data points or data, the fitting process compresses them into regression parameters that appear in the fit function. Now you told about how the regression is a function that describes the trend in the data or the shape of the curve, right? For a straight line, what are attributes that define shape? Think not clear?
Just
Okay. So what constitutes shape? Can you tell me for some simple functions, for a straight line, what are attributes that constitute or describe shape of a function, shape of a straight line or a linear function? Slope, also sometimes the intercept, right? That's why we write y equal to a naught plus a1x describes both slope and intercept. So the data is compressed in two parameters. For a second order function, what are some of the attributes of the shape? We express this as y equal to a naught plus a1x plus a2x squared. In addition to intercept, slope, it also has a curvature parameter. I mean, not often we give names to these parameters, but at least for the second order function, we can say there is a slope, there is an intercept. Sorry, there's an intercept, there's a slope, and a curvature parameter. Okay. If I talk about a function that falls exponentially, what is a parameter that describes how quickly this thing falls? If I were to write some function y equal to exponent of minus ax. What does this a denote? How quickly it decays. Anybody remember the word half-life from your physics classes? What is half-life?
Think about many times looking for high on the breakdown.
That is, if you started with some amount of atoms, what time does it take for it to drop by 50%? Right? That is half-life. That is how soon that it drops. This is basically you can solve for half-life by saying by saying this drops by 50%. So every function or every type of data has some patterns, and the skill we really need to exercise is to understand what type of mathematical function describes a given data set. And to do that, to say that this data set is best described by a linear or a quadratic or an exponential or a sinusoid or whatever function, you can't do that a priori. There is no magic rule that helps you predict what function will describe it best. It comes through practice and trying a few things and iterating. Okay. In most of this class, we make a guess, we iterate. If we are wrong, we fix it and we move forward. There is no one-step answer in most of the cases. Okay. So we are going to illustrate this fitting process through linear regression because it's the simplest form of regression. We'll start there. We'll learn some of the quadratic regression and we'll learn some of the other exponential and some other complicated shapes. Okay. So let's do that by, can I erase this side? So here is a, let's say, listen please, no need to write. So here is some data points, okay? And we want to ask if y fit a function of x equal to a naught plus a1x. Is this a good fit for the data? That's one of the questions we want to ask. And how to choose a naught and a1. These are the two questions we would like to ask. How to choose, and then how to ensure that choice is a good choice. Okay. So towards the end of last lecture, I told you that if you take y of xi minus yi, what is this quantity? Y of xi minus yi. What is this quantity? So let's say you have data points that I plot, okay, on a graph, and then I fit a straight line, which is going to be y of x equal to a naught plus a1x. So this is xi. We'll consider this to be xi, and this value for this data point, the corresponding value is yi. At the same xi value, this line also predicts y of xi. Actually, maybe I should draw this little exaggerated. Put this point here. So this is yi, and this value here is y of xi. What is the quantity y of xi minus yi? Can you interpret that in terms of what you see on the graph?
Given value of the point and what the line predicts.
It's the difference between the truth and what you want it to be. Right? So y of xi minus yi is like the difference between the fit value minus the true value. Fit value minus true value. And if it's a good fit, this difference must be small, if not zero. Right? A good fit, an ideal fit will minimize this difference. An ideal fit will minimize this difference. And it's not enough if we minimize the difference for any one particular value. We need to minimize the difference across the board for all values of x and y pairs. Right? We want to minimize it across the board. To do that, let's say n is the number of entries or pairs of x and y in the data. So n is the number of rows. So we have I equal to 1, 2, 3, 4, 5 up to n. So we have n rows of data. Okay. So we have y of xi minus yi. We want to square that and then add up for every row or for all the data points. Why are we squaring it? Why did we not just take the difference and just sum it up? Why are we squaring it? What can you say that a little more clearly?
You get 8 of the negatives.
That is, we consider a difference below the line and above the line, they are both equally worse. That is, you want them to be as close to the line as possible. Being one side is not any consolation. Okay, so we want to make sure that they come closest to the line. So we square it so that we get rid of the sign. And let's call this quantity S. Okay, so y of xi is like writing a naught plus a1 xi minus yi the whole square. The last lecture I wrote it the other way, but since it is squared, the difference or the way I write it doesn't matter. I can write it yi minus y of xi or the other way. It's not, there won't be any material difference. Okay, so you have this quantity S, and the ideal choice of A naught and A1 would minimize S. The ideal choice of A naught and A1 would minimize S, and that is where we get the name least squares regression. So you take the squares and you take its least value or the values of the fit constants, which will minimize S. Okay, so then to solve for A naught and A1, generate two equations, one by making it minimum with respect to A naught, and the second to make it minimum with respect to A1.
What would you describe S as? A variance?
Sum of squares. It's not variance because you're not correcting for the size of the data set. It's just sum of squares. Okay. So I want to, this is what I asked as the participation exercise from last lecture. So if I take this expression, and I differentiate with respect to A naught, I'm going to get 2 times I equal to 1 to n A naught plus A1 xi minus yi equal to 0. So that is like writing A naught times n plus A1 times summation I equal to 1 to n xi equal to summation I equal to 1 to n yi. Take a moment, look at this and make sure you understand how I got here. If you are not clear, please ask, we'll talk. Yes.
How does the n get multiplied to the first a naught term?
So good question. So you have this is like saying sum of an expression. So I break this into three summations. Okay. The first term is a naught is a constant. It is a naught counted n times. That becomes n a naught. Okay. Second term is a1 multiplied by sigma xi. So it's just it's the sum of all the x values taken vertically, and sigma yi is the sum of all the y values taken vertically. And we'll do this by example. Okay. Yes.
I thought this was multiplied by -1. You had on the board.
Last time. So last time I wrote yi minus y of xi. And this time I have y of xi minus yi. But neither should be important because we are anyway squaring it, so the sign doesn't matter. See, think of it as like this. Look here. This height and this height. One is below and one is above. If you call one positive, the other has to be negative. But which one you should call positive, that's a matter of convention. So it's okay to call this positive and the other negative or the other. Okay. Are we all okay with this expression? Everybody is able to look at this and go, yes, that makes sense. I'm on board. Okay. So then, so this is, if you look at it, n is a known number. This can be computed. This can be computed. So this is a linear equation in a naught and a1, two variables, which means you need a second equation. This is just one equation and two variables. Okay. To get the second equation, we differentiate with respect to a1. So this expression differentiate with respect to a1, that would be 2 times summation a naught plus a1 xi minus yi times xi equal to 0. Why did I get this times xi? Because we are differentiating with respect to a1, and a1 has a coefficient xi. So when I differentiate this, if this goes away, this has to remain. So I get xi. Okay. So if I rewrite this, this is going to be summation a naught xi plus a1 xi squared minus xi yi equal to 0. Call this equation 1. So I'm going to take this. So this is like writing a naught multiplied by summation xi plus a1 multiplied by summation xi squared equal to summation xi yi. So this is our second equation. This is a quantity that can be calculated. This can be calculated. And this can also be calculated. That is, if I give you xi, yi data, you can get everything that appears in these equations, and you can solve for a naught and a1. Are we okay? Yeah, do an example. Okay. Problem 17.6 from the book. I'm going to write it so that you can do. There is a formula for A0 and A1 that the book gives you. I don't like the formula because it's too big to remember. If I am given two equations with two unknowns, we can all solve it any day we want. We don't have to memorize some formula. Okay. So you have xi, yi. This is problem 17.6. This is the data. Okay. 7, 2, 10, 8, 11, 7. This is the data that's given to you. The usually a very simple problem like this will start like develop a linear fit for this data. So you have to solve for A0 and A1 and we'll see how. Okay. So what I'm going to do is to write A0 n plus A1 sigma xi equal to sigma yi. And I'll erase this. By the way, what you have here right now is the response to the participation exercise from last lecture. So you could just snap a picture of this and upload it if you haven't already done that. Like for the last lecture's participation, whatever is on the board right now is what I asked. If you haven't already done it, please snap a picture, write it up, upload. I saw the grade book. Most of you have been doing the participation. You don't do, you will fall back in the grading curve. So please keep doing that. Okay, and how do we start? This is your exam. You're given this problem. How will you set it up? Yeah, for now, let's assume this is a linear data set. We are still like this is linear. I'm telling you that. I'm asking what steps should we follow to get to the answer without confusion. This is exam, pencil paper. So without that, without graphing, how will we do it? Okay, so you want to draw a graph. What are we trying to accomplish from the graph? Like visualize the data. So it varies from 2 to 20. Let's say 2, let's say 20. And the y value varies from about 1 to 12. 1 to something like 12. But yeah.
I was gonna say we could start summing up the X on the Y.
You start seeking the numbers that you need to solve for A0 and A1. Okay. Start getting the numbers we need or the numbers needed. In fact, for this practice problem, yes, you're going to do that manually, but in the exam, these numbers will be given to you. And then there is some other trick we'll try to play. Okay, so that's the next layer. But let's learn how to do this. So what do we need? We need sigma xi So you need to sum up all of this. You need sigma yi, you need sigma xi squared, and then xi yi. So how you would want to write this is xi squared, yi, xi yi. These are the quantities you need. So let's say sigma xi squared, sigma yi, sigma xi yi. It's a little tedious, but there is no other option at this point other than doing this with Excel. So let's quickly do this. Can we get sigma x? Getting 91. Kindly confirm. So sigma xi squared, we need to square this. 4, 16, 36, 49, 100, 6. How much is 17 squared? 289.
Yeah.
289, 400. Can we get the sum, please? 20, 56, 56, 105, 205, 20, 26. One to one. Yeah. So sigma y. $52. Like 52. Yeah. 31, 40, 52. Okay. Sigma xi yi. Uh, 680. So these two equations will become 91 A naught plus 1211 A1 equal to 688 and 9 A naught plus 91 X A1 equal to 52.
So you said
So you have two equations, two unknowns. You can try to solve that fraction. You guys can solve and tell me. A naught. So in the exam, you won't be made to do this long calculation. I will provide you all these numbers. I'll provide you all these numbers, like all the numbers you will need, and you will have to use the formula correctly, get here, solve for A naught A1, for which you can use your calculator. You don't have to go through like Gauss Seidel or anything. You just use your calculator. A naught A1,
0.139.
139, 1390, and A1,
0.557677.
5577. Can I get somebody to tell me or give me an application of where we might use this? Any situation you can think of where such linear fitting might be interesting to you or needed to know? In your lab courses, have you done it? Yeah,
Would you like stress strain for a,
stress strain curve
yeah, but for the elastic region?
in the elastic region. So in the elastic region before yielding, it's still linear. So we would essentially have sigma equals E times epsilon. And in the lab, what quantity will you actually be measuring? This is of course stress and strain, which are kind of theoretical constructs. But what exactly in the labs, the raw data that you will be measuring? For stress, what is the marker of stress? You're doing tensile testing. Load, right? You will have a component and you will hang a weight on it and see how much it extends, right? So stress is measured as load per area. And what is the marker for strain? Deflection or extension, right? Delta L divided by L, right? So you will try to see if there is a linear relation between them. If they are linear, then you know it's in the elastic region. In any of your lab courses, have you done calibrations? Have you calibrated any instrument against the standard? Yes, no? No? Okay. I thought by this time we would have had that in the syllabus. It's not your fault.
Considerations, known values, but not already in functions.
Okay. So how many of you have used thermocouples? Can anybody tell me how exactly the thermocouple gives you a temperature readout? What exactly does it measure and how do you get a temperature readout in the end? Yeah.
They measure voltage, right? Or they give you a voltage readout?
They actually sense the voltage because if you bring two dissimilar materials in a temperature difference, it will produce a voltage. And that voltage is calibrated against a temperature standard to get you temperature. So if you take, let's say, for example, a K-type thermocouple, what do you measure? You sense a voltage difference. Okay, that voltage difference goes into a calibration function. So calibration is essentially a relationship between the temperature difference and the voltage difference. So if you measured, let's say, a voltage difference of 1 millivolt, it will tell you the temperature difference is, let's say, 10 degrees Celsius. And this 10 degrees Celsius is with respect to ice point or something like a reference temperature. So then the instrument is already programmed in with the calibration relation, which is nothing but a fit function. It could be a more complicated fit than linear, and that gets you a temperature. So the most important application of regressions is in calibration. You can't do calibration without understanding the fitting process. Okay. So I'm working on a engineering measurements course to be offered like a 4-6 elective, hopefully next fall or next spring. If you happen to talk to the chairman, tell Dr. Ranga has a course coming up, please offer it. Okay. Anyway. All right. So we have our fit constants. Now, for some of you who are going to work on projects that involve data collection through an experiment, like the experiment that I mentioned the other day. What was my experiment? I have a bottle that is fitted with a nozzle. Okay, and when I invert the bottle, the water is going to flow out, and I'm going to measure the volume reading as a function of time. So I'm essentially going to say volume and time. So it starts at some volume. Let's say it starts at 200 ml and it falls to 20 ml. And I'm going to record data at what time it crosses different volume points. So what is my raw data? My raw data is volume level reading and time. So how to get flow rate from this data? How would I get flow rate from this data? I know you're mouthing it, say it. My raw data will look like this. It will have time and it will have volume. Okay, so I start at 0 and I am at 200 ml. And every time I cross 20 ml, I record the time. So this is the raw data that I'm going to collect. Okay, from this, how will I extract volume flow rate? Divide which value by time? Which volume? There are like 20 different volumes.
The change in volume by that's what.
Okay, that is one way of doing it. What she's saying is take some particular value and divide by time. How about if I fit a linear curve to this and take its slope? The slope would be Q. Right? The measurement I want is to take the rate of change of volume with time, which is best described by the slope. So if I plot my data as time versus volume, this is my X data and this is my Y data. If I fit a straight line, my slope is the measurement that I'm looking for. Okay, everybody is with me? What is like a application of this thing we're learning? Here is your participation exercise for today. If I am trying to measure flow rate, I'm taking volume, I'm taking time, and I'm fitting a straight line, getting the slope. Now this measurement has a certain uncertainty. How? If the data were really linear, I would get a very consistent slope. If the data is not linear, or if I'm not very good in my data collection, I was not paying attention, checking out my phone, was distracted, all kinds of things, the scatter in my data will be very bad. It's like the difference between doing a good experiment, being diligent, and being a lousy experiment. If whether I'm lousy or whether I'm good will reflect in the quality of the data. Okay, so not only is this slope important, what is also important is the uncertainty in the slope. Do you agree with that? The uncertainty in the slope tells me about the quality of this measurement. So the participation exercise for today, find out how to get a fitting or statistical uncertainty in the slope and intercept. You can consult any source you want, any textbook, any internet source, any AI. Ultimately, if you get that information and you can continue basically from here, just say you got A naught. I want you to get the uncertainty in A naught and the uncertainty in A1. This is crucial for your project piece because those who are doing measurements, you will fit something, you're going to have to report the uncertainty. This is how you do that. What was your question? What page is this question on? I just made it up. It's not in the book. So find out that information, please write it up on paper in your own handwriting and upload it for today's participation. Okay. All right. So we learned one skill, right? We learned how to do linear fitting. Now we'll try to use that linear fitting many times over to tackle few more problems. Okay. So let's do. If you have the book, problem 17.8. Problem 17.8. You know, problem 17.9. Problem 17.9, 0.4, 800.8. Okay. Let's say our data set looks like this. What is the big difference between this data set and the previous problem? Just look at the X and Y value and how much they range and tell me what's your first impression. To help you recollect, the previous problem, X varied between 2 to 20 and Y varied between 1 to 12. In this problem, X varies between 0.4 to 2.3 and Y varies between 800 to 3,600. What's your first impression?
Y is a lot bigger, it's a lot smaller.
In this case, there is the disparity between X and Y is quite high. Okay, that's one. What else can we say? Look at the range 2 and 20, 1 and 12. Look at the range 0.4 to 2.3 and 800 to 3,600. Just think of how much bigger this is than this. How much bigger is this than this? 20 minus 2, the range is 18. 12 minus 1 is 11. Okay. Over here, this is 2.3 minus 0.4 or 1.9. Here the range is 2,800. What can you say? Slope will be a lot higher. That we already kind of say because Y values are much larger than X values. Not only is that true, if you see here, 2.3 is about 6 times bigger than 0.4. Is about 6 times bigger. Okay, 3,600 divided by 800 is how many? About 4 times bigger. Right. 4.5 times bigger. About 4.5 times bigger. Okay, the scale here jumps nearly from an order of magnitude. That is, this value and this value have different ranges, whereas these two are similar. So this variation can be called linear, whereas this variation is logarithmic or exponential, depending on how you see it. It's like if we all take our median incomes, all regular blocks, we'll all be in the same ballpark. Suppose you bring Elon Musk into the same graph, where do you get the term off the charts? It's because one value is so extreme, it's so far away in the graph, it's off the charts, right? So when you have values that are nothing like the earlier values, you can't have a linear scale. The scaling has to be something else, like an exponential or power law scaling. So a data set like this cannot be fit to an equation that looks like y equal to a naught plus a1x. It won't fit. It will fit only part of the data, the other part of data won't be fit. We need to transform for exponential or logarithmic data, which can be x, y, or both. We need to transform the data before applying a linear fit. Before applying a linear fit. How do we do that? Okay, so how do we do that? If x and y don't have a linear scaling, check if ln x and y or x and ln y or ln x and ln y have potential linear scale. So which one should we pick? What's your intuition? Louder, please. X and L and Y. But why did you say that? So I think his intuitive reasoning is these are big numbers. If you take their logarithms, you will get small numbers. These are already linear in their range, so you don't have to do anything. So we are going to go with x and logarithm of y. So you have x, we'll call the new y, the logarithm of old y. And what we're going to do is to transform the data into this new form and then apply linear fitting to this new data set. Everything else is the same. How you get the constants, everything same, except we are going to do this with transformed data. So the transformed data I need some help here, or actually I can open Excel and do this. So who has the question? Should I use natural logarithm or logarithm to base 10? Is there any particular base that we should use? Does it matter? Can it be either? And you'll still be able to get the nearly the same equivalent results later. We'll see. Okay. We'll go with ln y and I'll tell you later what's the best choice. So if I do that, I'm getting values 6.6846. Anybody has it? Can you help me? Thank you. 6.8824.
7.3132. 7.5756. 7.9725. 8.1887.
Thank you. So look here. Previously, it was a very wide range from 800 to 3600. Now it's actually compressed from 6.68 to 8.18. It's now much compact. You can easily fit a linear. And the other values are 0.4, 0.8, 1.2, 1.6, 2.0, 2.3. Yes.
First, now let's see what we do. X.
Yeah. Oh, yeah. Oh, that is my 4. Sorry. My apologies. Okay. I'm going to give you 5 minutes to work out the fit cost. That is, I want you to develop a fit y equal to a naught plus a1x. Please get me a naught and a1. I'm also going to do that using Excel, but you do that with paper and pencil, and let's meet again in 5 to 10 minutes. So until you get a naught and a1, you can forget about the old data set. This is your data set. Let's solve for a naught and a1 like I showed previously. And in the exam, this table and these values, the log values, I'll be providing. I'll also provide this information. Okay. Sigma xi 3.3. Sigma yi, which is 44.6170. 6170. Sigma yi, the uppercase y. Okay. And then sigma x squared. 14.09. And then sigma xi yi, uppercase y, 63.8555. All these will be given to you. It won't be that easy in the sense, only this will not be given to you. I'll give you ln x, I'll give you ln y, and you'll have to choose which transformation to use. Like we made this choice, right? X and ln y. You could have very well chosen ln x and y if you didn't know how to choose. So I'll provide you more information than you need, but you have to pick out the right information. So now can we solve for A0 and A1? A0 times n being 6 plus sigma xi A1 8.3 A1 equal to sigma yi 44.6170 and then 8.3 A0 plus 14.09 A1 equal to 63.8555. That is A0 n plus A1 sigma xi equal to sigma yi A0 xi plus A1 xi squared equal to sigma xi yi. You have A0 and A1? Yeah, I thought you were ready.
I think A0 6.3
A0 is 6.3
036
036. A1 is
0.8187.
8187. Is this what everybody is getting? Thank you. Everybody is getting these values, A0, A1? Yeah, good. So the problem is still not done, which means look at this equation, look up please, take a pause. If you look at this equation, what we have written is ln of y equal to A0 plus A1 x. That is, this y is nothing but logarithm of the original y, right? So what I can do is I can write y equal to exponent of A0 plus A1x or exponent of A0 times exponent of A1x. That's like writing exponent of A0. That doesn't seem correct. Exponent of 6 is a huge number. That's exponent of 6.3. Yeah, okay, that's not bad. That's only 540. So maybe it's not a problem. Okay, what is exponent of 6.3036? That's 546.5359. 546.5359 times exponent of 0.8187x. So this is the equation that describes your original data. And how do we check that? We can pick this equation, plug in any of the x values and see if you get something that is close. So let's try for 1.2. Y of 1.2 is 546.5359 times exponent of 0.8187 times 1.2. What is this number?
1460.
Come again?
1460.
1460. 1460. We have 1500. Is that good or bad? 1460 and 1500. How do you make a judgment whether that's a good, reasonable approximation or not?
100% error and it's within your criteria.
This one is 10% of 1500 is like 1350. So if you are within 1350, you are 10%. If you are within 1425, you are 5%. So we are within 5% here. Between 0 to 5%. Okay. We'll do one more problem before we start discussing goodness of fit and how to judge whether a fit is to be accepted or rejected. Okay. We'll do one more problem in solving for A0 and A1 before we get to questions. Something not clear? Problem 17.12. You have the book, problem 17.12. Give me 1 second here. I'm going to bring that up on the screen. Because okay, we are looking at problem 17.12. We know only one tool, linear fitting. Somehow we have to reduce every problem to linear fitting. That's our mission. Okay. So look at this. The growth rate of bacteria K per day as a function of oxygen concentration C in milligrams per liter is known to be modeled by an equation that looks like this. K equals K max times concentration squared divided by CS plus C squared, where CS and K max are parameters. Firstly, use a transformation to linearize this equation. Then use regression to estimate CS and K max and predict the growth rate at 2 milligrams per liter. Here's your data for C and K. You have to fit this data to this function. How do we turn this into some kind of a linear equation? That's the process they call linearize. Before you answer this, in your lab courses again, was there any instance where you measured a quantity, but instead of plotting that quantity, you plotted its inverse or squared or something to get a linear relationship? Can you recall anything like that? Okay. So you approximate it as a linear gradient in temperature. Okay. All right. But there you measured temperature and you plotted it against distance. So you didn't have to linearize it. It was linear to you, for you.
If it's actually.
Okay. How? How did you linearize? Yeah, I need more context, but we can talk about it. Okay, if people don't have examples, that's fine. Have you done this experiment to verify Boyle's law? PV equal to constant. Okay, if you're curious, go look that up. Okay. Okay, how do we linearize this one? Coming back here, how do we turn this into a function which is something like y equal to a naught plus a1x? In k is your measured or dependent variable, c is the controlled or independent variable. In what form should we plot this so that you can get a linear equation starting from here? That's the question. I just want some initial thoughts. If not, I can show you how to do this. Yeah. Do we have the data copied, please? Problem 17.12. Okay, please copy the data. This is 5 entries, and then we'll do. All right, problem 17.12. K equals K max times C squared divided by CS plus C squared. This is the equation, right? Yeah. Okay. So to linearize, first you need to recognize what can you do to turn this into a function that approximately looks like a naught plus a1x. So what if I first step invert this? 1 over k is cs plus c squared divided by k max times c squared. Can I do this? Right, just inverting it. And then once I invert, I'm going to write this is 1 over k max multiplied by cs over c squared plus 1. Cs over c squared plus 1. Okay. So then I'm going to write k max times 1 over k equal to cs over c squared plus 1. Actually, no, sorry. What I will do is this. 1 over k equal to cs over k max times 1 over c squared plus 1 over k max. That's it. What if I call 1 over k as y, 1 over c squared as x? This quantity, I'll call it a naught or a1, and this quantity, I'll call a naught. Can I do that? I'm just labeling variables to say my new y is 1 over k. So my original data looked like this. I have c, I have k. I'll define x equals 1 over c squared and y equals 1 over k. Okay. So once I do that, I have once I do that, I have y equal to a1x plus a naught. So y is 1 over k, x is 1 over c squared. A naught is 1 over k max, or k max equal to 1 over a naught, and a1 is equal to cs over k max, or cs equal to k a1 times k max, which is a1 divided by a naught. The goal of any fitting exercise is to eventually get the parameters that you care about, K max and CS. So ultimately you do some intermediate steps, but convert it back to what you were originally seeking, K max and CS. So this C and K values are given to us. There were like 5 entries for C and K. So using that, you compute X and Y. From that, you do linear fitting. That will get you A naught and A1. From A naught and A1, you get CS and K naughts. That completes the fitting process. Question: how am I supposed to come up with this brilliant scheme to invert it, do some manipulation, and rewrite it? What is the idea behind that step? That's the big question. Because if I just give you a table of data and I don't give you anything else, how are we going to do this? How will we magically end up with c squared and k max and everything? In practice, people who do this work, they would try plotting the raw data in against many different variables. That is, let's say you collect two quantities, x and y. It's not always that x and y will have a direct relationship with each other. Maybe x squared and y will have a relationship, or 1 over x and y will have a relationship. They might be in some combination. That is part of developing your intuition about that little problem. At least for our course, this sort of an equation will be given to you, and then you are asked to linearize. But in your actual project for the course, you might pick up two variables whose relationship may not be obvious. So you'll have to play around to figure out which transformation will work for you. Or there may be some physics principle that guides you. Okay. Let's try one more exercise in linearization. I'll give you a function. You just have to linearize. And once you do that, the rest of it is probably doable. Okay. Problem 17.14. Just the linearization part. Problem 17.14. Y equal to a plus square root of x whole squared, a plus square root of x divided by b times square root of x, the whole squared. Linearize this and get it to a form where you can write y equal to a naught plus a1x. If I take this equation and take the square root of both sides, square root of y equal to a plus square root of x divided by b times square root of x. right? And if I divide each term by the denominator, I get a over b times 1 over square root of x plus 1 over b. Yes,
Did you do the one?
I just divided the numerator by each term of the numerator by the denominator. Usually that is your clue. If you have an expression that has a single term in the denominator and multiple terms in the numerator, get it to this form so that you can divide it term by term. So you call this your new y, you call this your new x, you call this your new a naught, and you call this your new a1. Sorry, it's a little mashed up, but you get the point. So if your original data is provided in terms of lowercase x and y, that original data is not useful because that function looks like a quadratic or some kind of function. But if you plot it in terms of square root of y and 1 over square root of x, that is this data, when you plot this as 1 over square root of x and square root of y, it will look like a linear data set. So square root of y equal to a over b 1 over square root of x plus 1 over b. This process is called linearization, turning something that doesn't look like a linear obviously into a function that is linear when you plot it in terms of some special variables. Yes.
How do you know that the slope is negative?
Well, if you take x values that are large, 1 over square root of x will be small values. Those will be mapped onto the smaller portion. So let me look at the data here. So the data here given in terms of x and y, it varies from 0.5 to 4, 0.5 to 4, and y values vary from 10.4 to 10.4 to 2. So the original data looks something like this. So maybe I should have drawn it this way, but my point is it is linear. I have 5 minutes. I want to address some issues or questions related to the project. I had a few come up to me and say that they were going to do like a simulation to generate data and then test some hypothesis using that data. For those who want to use simulation as an experimental tool, that is, you want to run a simulation and use it as a test, as a way to make data, the bar is slightly higher in the sense, let's say you are trying to simulate the motion of some objects using Newton's law. You solve F equals ma to solve billiard ball equation of motion or the equation of motion or something. You can't also test is F equals to ma from the same data. You can't take the assumptions that you use to generate the data and make that part of your hypothesis. Okay, so a good example would be to have a stochastic simulation. Let's say you are trying to simulate the outcomes from a toss of a coin, and it's an unbiased coin with 50% chance of getting head or tail. You simulate a sequence of 1,000 coin flips. So you'll get approximately 50-50 of head and tail. Your hypothesis cannot be, is this coin biased or unbiased? Because that was one of the assumptions that went into generating the data. Then you can't also make that hypothesis. But if it were a coin that you found on the street, and for some reason one side is more polished or less polished, and you want to find out if it's an unbiased coin, you literally sit there and flip it 1,000 times, and then you use the data to test whether it's biased or unbiased. That is acceptable, because that is like you are taking a coin which you don't know, generating data and testing a hypothesis. But if you created a computational universe, you put in assumptions, you programmed how the balls will move, you can't use that data to again test something like the equation of motion. So people who do computation or want to do computation, you should clearly explain the equations that go into your program. You have to show me clearly what equations are being programmed, what data is being generated, and then I'll check if that hypothesis is actually a meaningful one to test. This is for people who do computation. People who do experiments, you have to clearly describe the steps or method that you will follow for your experiment and what data will actually come from the experiment. In my example of that feeding bottle experiment, even though I said I want to measure flow rate, the raw data coming from my experiment would be volume positions and time points. So you should be able to clearly tell me what is your raw data and how you will reduce that to some kind of a quantity and then a hypothesis. Okay. And then people who do surveys, you have to first list all the questions you're going to ask. The questions should be well thought out. It should get data that has some relevance. Like, for example, it should not be something that is arbitrarily asking somebody like, how far do you travel each day for work, something like that, without context. If you just get data and then you don't have a connection or a story to which that data connects to, it's meaningless. So there are about 10 to 12 groups. It's not a big number, luckily. I would like to look at each project description, do some vetting, ask some questions if necessary, stop you, make you rethink. Only then, once I give the clearance, it means you have my approval, you can go and collect your data. But whatever you submit next Tuesday will be scrutinized. It won't be scored, but we'll try to provide you feedback. Okay. How many groups need like a session or want to talk to me but haven't made the effort because you're busy or for any other reason? If you want to come talk to me, I have availability tomorrow morning. I have availability Tuesday morning. So please, let's make sure we talk before you turn it in. Okay. Unless you're very sure about your project and the data collection and the hypothesis, I would strongly suggest everybody to come talk to me. Not assume that you would be automatically correct. Get it checked before you submit. The last thing you want is to spend 3 weeks, the next 3 weeks, working on a faulty experiment or a faulty hypothesis, and then realize you have to start over. Okay, let's not let that happen. So please come talk to me tomorrow. I should be here by 10 o'clock. I'll be in my office from 10 to 11 and 11:30 to 12. So please stop by. We'll have a chat. Okay. Thank you.